some generation. Okay, so any magic tricks? Does anybody have anything interesting to show us? No more. Nothing, Nick. Yeah. Up your sleeve.
Not today, but maybe next time.
Good.
Oh, thank you.
Okay, so what we want to do next then is we want to connect the statistical picture with the macroscopic world, and so we have to talk about thermodynamics a little. You know, I never liked thermodynamics when I took it as a student because you never really understood what was going on. It was just, right? You just had a box and things were happening, but you didn't know what was happening inside. Is anybody here who really likes thermodynamics? Anybody who really hates it? But typically people like statistical mechanics more than thermodynamics. Anyway, all right, so first law. What's the first law?
It's about
Conservation of energy. No. That just says energy is conserved. So the change in the energy of the system, dE. You guys have these notes, right? How many people have read the notes? Good. You read them? All of them? Some of them? Did you read till you? The other one. You read this one? Yeah. But if you get a chance, it's good to at least leaf through it, have some idea what's coming up. I always think of tough questions to ask.
I do the opposite. I go back and read it to understand what you said.
That too, yeah. It doesn't have to be either or. And
Or both.
or
Before and after, but it's...
yeah, before, yeah, and even during. Okay, so dE, the change in the energy of a system is the energy, the heat that goes in, minus the work that goes up. It's usually written like that, so this is heat in. And this is work done by the system. Okay, so this is just the conservation of energy. So you put heat into a system, energy goes up. And if the thing does work, then its energy goes down. So just conservation of energy. What's the second law?
About nature, the entropy goes down.
Entropy doesn't go down.
In nature.
In nature? We are always in nature. All there is. What?
The surroundings, entropy. I'm
That's
not saying
a
he's,
sentence.
I'm not saying he's right, but he said the nature of the entropy go down. I mean the surroundings entropy go down.
Because in an isolated system, the entropy always goes up.
Right. I think that's the thing. In an isolated system, the entropy doesn't go down. That's what it is. So that's important because, of course, if the system's not isolated, the entropy, of course, goes down. You know, you clean up your room, entropy has gone down. So, oh, the door locked. Maybe leave it open a crack in case others want to join us. Could happen. Okay, so it means that the entropy of an isolated system does not decrease. So ds, so S now stands for entropy. In an isolated system, the change is either zero, it stays constant, or the entropy increases. Ds is positive. And that's all we need. There's a third law too, involving entropy at absolute zero. I remember my advisor once said that the three laws are that you can't win, second is you can break even, and the third is you can get out of the game. One way to remember. Okay, so now some notions about work. So we think of work typically as force times distance, right? That's good. But there's other ways of doing work. You can magnetize something, you can electrically polarize something, that's still doing work. So there's a kind of a general notion of doing work. So usually we think of this as F dx. So we're using the same notation as I have. So this is work done by the system, and this would be force acting on the system. And so the whole idea, though, is that we can think of it not necessarily as a usual traditional force and traditional distance, but we can think of these as a generalized force and a generalized distance. So these could be generalized, and this could be a generalized distance. So for example, if it's a real force, then this is just a force, and this is distance. But it could be that you have something like PdV, where this is now, right, this is work, pressure times volume. And you can think of this as generalized force, generalized distance. It could be dV. Or it could be EdP. Could be an electric field, time change in polarization, or it could be HdM, where M is the magnetization. So I just want to alert you that it doesn't have to always just be traditional force and distance. It can be generalized. Okay, so that's it. So, okay, so we know this, and these are laws in the sense that we have never observed any violations of this, but we don't know why they happen. But that happened often enough that we have become familiar with them, and so we believe that they will keep on happening in the future, although we don't know for sure. Tomorrow the laws of physics may change. Hasn't happened yet, but it could happen. All right, so these are the laws, and then now we want to get to the ideas of thermodynamic potentials, which we can simply define and interpret in terms of these laws. So we can define thermodynamic potentials like the free energy. Helmholtz free energy, Gibbs free energy, there's different kinds of free energy. We just define them and then understand their significance by reflecting on the laws of thermodynamics. And let's start. Thermodynamic potentials. Okay, why are these interesting for us? They're interesting for us because they play the role of potential energy. In simple mechanical systems, we have potential energy. In equilibrium, the system minimizes the potential energy. gradients of the potential energy are forces that move our system towards equilibrium. Thermodynamic potentials, as we will show, play the same role for systems containing many particles. So they have the same role. They will be minimized in equilibrium, and their derivatives will give us generalized forces that push the system towards equilibrium. Okay, so main point is that these play the role of potential energy. And the first one that I want to introduce, and this is really the one that we'll be working with almost exclusively, is the Helmholtz free energy. And this is the one that physicists use, chemists use the Gibbs free energy, but we kind of look down on that. Helmholtz is better. But it turns out, in fact, that there are many different kinds of free energies that you can use, and depending on the constraints that you have in your system, some are better than others. The Helmholtz is good at constant temperature. Gibbs is good at constant pressure. So it just depends on what you want to use. So let's just start with the Helmholtz. And we simply define this. Okay? Just the definition, and then we find out its physical significance, and then we find out how we can put this to work. So the definition of the Helmholtz free energy is what? Who knows what this is?
U minus Ts.
Okay, good. But I will use E. So this is the average energy minus Ts. Okay, so this is the average energy of the system, this is temperature, and this is entropy. And at this stage, this is just a definition. It has units of energy, but it also somehow contains entropic contributions. And so, if you now look at what happens if we have a system where things are changing, energy can change, temperature can change, entropy can change. The change in the free energy is dE minus TdS minus SdT. This is kind of obvious. And now we can use the first law to replace dE. We can write the change in energy in terms of dQ and in terms of the work, right? So this is dQ minus dW, work done, minus TdS minus SdT. Now we have to say something about dQ, and we know that heat is connected to entropy somehow. What is the relation between entropy and heat? SdT. Yeah. dQ, ds is dQ over T. The change in entropy is the heat that you put in divided by the temperature. Now, when is this true? Is this always true?
For a system in equilibrium. Well, or for, how do you say, very slow processes.
Well, okay. If it's an
The one that
equilibrium,
can go
nothing is
back.
happening.
The one that can go back.
Right, that's right, very good. So this is true if the process is reversible, or reversible processes. If you can do something very slowly and gradually, then you can usually undo it also. You can have a box with stuff in it, if you heat it up a little bit, raise the temperature a little bit, heat will go in, cool it down a little bit, heat will come out. So in a process like that, reversible, this definition is true. There are many other ways that you can change the entropy of a system without adding heat. If you have suppose you have a big box that has nothing but vacuum inside, and you put a small bottle of gas inside, that's your system. But it's isolated, it's in a thermos bottle, no heat can go in. And then you uncork the little bottle of gas, gas comes out, runs around. It changes the entropy, but no heat has gone in. On the other hand, it's not a reversible process. So this relationship is only true for reversible processes, and it's good to remember that. But for reversible processes, then, we can write dq as TdS. And you see that these guys now cancel out. And we have that the change in the free energy is minus dW minus SdT. So we have assumed here that the process is reversible. If we then make another restriction, if we assume that the temperature is held constant, so the temperature is constant, then this term disappears, and then we have dF is equal to minus dW. So the significance of the Helmholtz free energy is that it is equal to the work done by the system at constant temperature. Right? This is the work done, this is the work done by the system. This negative quantity is the work done on the system. If you work on a system, its free energy goes up. So it's kind of like potential energy. The work on lifting something, its energy goes up. If you work on a system at constant temperature, its energy goes up. So dF is equal to the work done, or minus dF is work done by the system at constant temperature. So it really is kind of like potential energy, but it's very precisely exactly this. Okay, so then we want to ask, well, what happens if the temperature is not constant? So let me try to do that. If T is not constant. So let's imagine a situation where we have our system and we connect it to a thermal reservoir. Okay? This is a huge, I don't know, think of it as a huge piece of copper at some temperature. So this is thermal reservoir. This is our system. Now let's assume that the temperature of the system can change by having heat flow back and forth. No, I'm wrong. I don't want to say this. I don't want to say this. I want to, yeah, we looked at a situation, right, it has to, Right, I want to remove the reversibility condition. Okay, so we're not going to use now the fact that the process must be reversible. Okay. We want to understand what happens. So here's the system, here's a thermal reservoir, and heat can go back and forth between these guys, and we will allow the world to be in contact with the system so that work can be done on the system or by the system by something out here where there's no entropy change. So constant entropy. Now, what is a system that has constant entropy? Well, having a brick up here has the same entropy as having a brick down here. There's no disorder in the system. It's simply an energy storage device. So there's no change in the internal state. There's no entropy change associated with that.
And why do we want to have that entropy constant at that system that makes work?
Why?
Why?
Just so that I can make this argument.
No, I mean if it only does some work on our system, right?
Yes. But I want to talk about the entropy of the universe,
Oh, okay.
including this thing, right? And I have to worry about its entropy. I just want to point out that there are many systems where the entropy change is negligible even though the energy change. Okay. So the main point is that now we are no longer requiring that the process be reversible in our system. Okay, so let's do this. So from the first law, we can say that energy is conserved. So the change of energy of our system plus the change in the energy of the reservoir is equal to the work done on the system, which I would write as minus f dx here. Because I could write dw just as easily, but I'll write it like this. So this is just some generalized force, generalized displacement, and that is the work done on the system. So that's the first law. And then the second law says that ds plus ds prime must either stay constant or increase. So this is the world we are looking at here. This is an isolated system, and its entropy cannot decrease. And because the source of work has constant entropy, we only have to worry about these guys here. Okay, so now, even though this system may be undergoing irreversible processes, this is a huge system, so this is always close to equilibrium, and this heat flow is going to be reversible. So this guy, for this guy, we can write the energy change in terms of dq over t. So we can write that dE minus dE plus T ds prime minus fx equals 0. And then,
Not here.
yes, thank you. And then we can look over here and see that if I multiply this equation through by the temperature T, then I can show that TdS is greater than TdS prime is greater than minus TdS. And so if I replace this by minus TdS, then I have to put a less than or equal to here. So dE minus TdS minus FdX is less than or equal to 0. All right. And so now, this is T. So if T is constant, okay, so this reservoir can, of course, surround this guy completely. Then we have dF, change in the Helmholtz free energy of our system, is dE minus TdS, because SdT is going to be 0. And so this guy here is just the change in the free energy. And so finally we get that dF from over there is less than or equal to Fdx. So this is kind of the same as the result we had before, except we have an inequality here. And what this tells us is that the maximum work that a system can do on its environment is the change in its free energy, but the work can be less than that. So we cannot do more work than the change in the free energy, but we can do less because the free energy can change without doing any work. So F, measure of the maximum energy, maximum work, maximum work that can be extracted from the system. Okay, so what have we done so far? We introduced a quantity, which is the Helmholtz free energy, E minus Ts, and its significance is that it is a measure of the maximum work that the system can do. Okay. The system can never do more work than that. It can certainly do less work. Okay. So, and maybe the most important point is if there is no work, so the system is not connected to some energy absorbing thing, then the change in the energy is less, the internal energy is less than or equal to 0. So that means if you just leave the system by itself, its free energy either stays constant or is decreased. That's all it can do. So if the system is not in equilibrium, its free energy is going to decrease. So if you have a liquid crystal and you do something to it, align it all somehow with an electric field, say, and then you remove the electric field, its free energy will either stay constant or it's going to decrease. And it's nice to put a dt here because it means that the free energy of a system will decrease in time. And it will keep doing it until it doesn't do it anymore. That means that in equilibrium, when nothing happens, the free energy must be minimal. In equilibrium, F must be minimal. So that's really maybe the most important thing, is that if you have a system which is out of equilibrium, the free energy is going, and it's not doing any work, you're not doing work on it, it's going to move towards a system of minimum free energy at constant temperature. Okay. So the significance of Helmholtz free energy is that if you want to know what happens in equilibrium, we must minimize the free energy. And this is going to be a kind of a guiding principle for the next part of the course. We'll be constructing free energies and minimizing it, because that's what the system will do. So we now understand what F is. It's E minus Ts. We have yet to connect it to our statistical picture, to the Boltzmann distribution, but we will do that for the next lecture. And then we'll pretty much be ready to go to work and start applying this structure to different physical problems. Okay? Thank you. So